Thank you for the introduction. We will change material and moving to aluminium material. So I'm Armelle Daniélou. I work for Constellium. Constellium is a producer of aluminium, especially for aerospace, automotive, and can stock. And I will present to you possible interaction between aluminium and hydrogen. And you can see the name of the people that have participated to this presentation. So aluminium is today a good option for the space launchers and for the civil aircraft, for the tank parts that contain the propellant, so mainly the hydrogen, oxygen, or methane. And he has excellent cryogenic properties and low density. His main advantage also is the high recycling level. And today, some specific alloys are already used for the space launchers. These are 2000 series, such as 2019, 2195, and 2050. The last two contains lithium. I will come back to that later. For this application, we can consider different possible interaction with the tank. So hydrogen, either in gaseous or liquid form, is in contact with the tank. So first in liquid, it's cryogenic temperature. So we need high resistance to low temperature. And we need also a low permeation to hydrogen to keep it inside the tank. We may imagine that during the filling step or the reheating of the tank, there could be some water or water vapor that can lead to presence of monoatomic hydrogen that could then be absorbed at the surface. Hydrogen can be generated by corrosion and then enter the metal. This effect can be simulated through stress corrosion crack trials in hot, humid air or in a chloride environment. So concerning permeation, here is a bibliographical survey conducted by David Schultheis. You can see different, so gather different data on permeation for aluminium in pink, steel, stainless steel in blue, and composite on the other color. You can see that at room temperature, the permeation of aluminium is very low. And if we make an extension with the Stewart law to look at very low temperature, you can see a strong decrease of permeability. And at 20K, so operating temperature for hydrogen tank, the permeation is virtually nil. Concerning interaction between dry hydrogen and fatigue, we have a few data in the literature. So here is presented data from Matsuoka on comparing fatigue crack growth rate in air or under hydrogen with a pressure of 150 MPa. So different aluminium alloys have been considered, either a 5000 series, 6000 series, or 7000 series. As a general view, we have a decrease of fatigue progress when the metal is tested under hydrogen versus in air, which is attributed to the water film deposition that can appear in air that's supposed to be a little bit humid, and that was not the case for hydrogen that was dry. If we then consider that we may have hydrogen in a monoatomic status, we have to consider environmental assisted cracking. And it's a general term. It englobes hydrogen enrichment either with gaseous hydrogen or humid air, or also hydrogen coming from corrosion. So there is an overlap of corrosion and hydrogen enrichment terms. And we will have a look at the common part that can be tested through stress corrosion trial under humid air or with chloride presence that will enhance the decomposition of water and enable the hydrogen to go inside the metal. We have conducted a study on different aluminium alloys. So first 7,000 series. So for that kind of aluminium, we have principally as a main addition element, zinc and magnesium that forms the hardening phase. We also have considered 2219, which is an incumbent alloy for space launcher. It has a high level of copper. In fact, it's above the solubility limits, which could be improved. We have considered incumbent 2024 for fuselage application in aircraft, and also 2050. So that is a lithium containing alloy. Around 1% lithium is added to the composition, and that reduces significantly the density. Between 2050 alloy and the 7,000 series, we have a decrease of density by around 4% to 5%. That could be seen as a low value, but when you want to increase the payload for the launcher, or if you want to add one passenger in the aircraft, it's important. For the stress corrosion trial, we have chosen two types of tests. First one is a hot humid air, so metal is put in a constant humidity at 85% of relative humidity. The temperature of the test is quite high at 20 degrees. We also conducted some trials at a lower temperature at 50 degrees. The specimen are around 3 millimeter for the diameter. They are stressed in the short transverse direction, that is to say the thickness of the plate. And the stress is 85% of the TYS. And we also conducted trial with varying stress, and this is done at constant load. The other trial is with the chloride, so 3.5% chloride. It consists of alternating immersion during 10 minutes and immersion during 50 minutes, and then we go back to immersion. The temperature is close to room temperature, and then the way we load the sample is similar to the other test. So reminder, the general description of what happens during corrosion in 7,000 series in hot humid air. So corrosion may enhance hydrogen generation that will permit hydrogen to penetrate the metal, and then it can go to grain boundary, create embrittlement, and then there is a propagation of both crack due to hydrogen embrittlement and corrosion. In hot humid air, some crack arrest markings may be observed. They are also observed in sometimes in the under chloride test. So these are the line here. So that's a failure path after rupture of the sample, and these lines correspond to high containing oxide. It is difficult to sew them. You have to be at very low voltage, and you don't have to clean the surface before observation. If you want more analysis on this phenomenon, Meti Frexis has done an in-depth study of what happens during corrosion of 7,000 alloys, and he has studied in details the. So I go further. So in hot humid, there is a strong effect of plate thickness on the 7,000 alloys. So the lower the plate thickness, the lower the stress resistance, which can be attributed to change in grain size and also quench properties. When you overage the metal, you also have a big increase of corrosion resistance. So 7,000 series are overage, but when you go from T76 to T74 jumper, you increase the aging duration, and that is beneficial to increase the resistance to stress corrosion. This is also observed in a standard chloride test. And when you change the stress, you also change the resistance. So the higher the stress, the lower the stress corrosion resistance in both tests. Temperature is also an important factor. When we test at 70 degrees, the test is more severe than at 50 degrees, but even at 50 degrees compared to the tank application that are as in long part of their life at cryogenic temperature, these remain a severe disease. We have compared 7,000 series to 2,000 series, and it appears that 2,000 series, so 2024 in T3 temper without aging, 2050 and 2219 in T8 temper, so at peak aging, they have no failure after 200 days, so they are quite immune to stress corrosion crack in hot humid air. In a cryogenic temperature, 2000 series also exhibit good behavior. So it is known that the yield stress increases when temperature decreases. It's more difficult to predict the evolution of toughness because it depends on many parameters. The TYS increases, but also the strain hardening and the stress on grain boundary is also modified at low temperature. For this alloy, we observed both increase of yield stress and toughness when the temperature is decreased down to cryogenic temperature. Copper lithium alloys are already used in launcher. So here is an example of the location where they could be used. So mainly in the tanks. So you can see the tank here. You have a cap and you have a cylindric walls, and the hydrogen is included in the tank. There are other possible utilization of lithium alloys, mainly in the upper stage, for which the payload increase will be more important. So as a summary, under hydrogen gas, aluminium is virtually insensitive to environmental effects. In humid condition, we may have some sensitivity for 7,000 series, but it strongly depends on the temper of the material, on the thickness, and also on the stress that is applied. And 2,000 alloys appear quite immune versus this kind of solicitation, and that's the reason why they are good candidates for space, but also for aircraft application. Thank you.